Hello everyone, my name is Alvaro, and in this video I will be solving another problem from the blind Leetcode 75 problems list. Today we will be doing problem 102, which is called binary tree level order traversal. And this is a tough one. I have not been asked this one on interviews, but I know of friends that have gotten this question when interviewing for Amazon and Facebook, so definitely one to keep an eye on. So let's read the problem statement and then the code, and let's get to work. Given the root of a binary tree, return the level order traversal of its nodes' values, which means from left to right and level by level. Example 1, we have this tree, and the output is, a sublist, so 3, 920, and then 15.7. If the input is just one node, then we return a list of a list still. And if the root is empty, then we just return an empty array. Okay, seems fairly straightforward. The implementation might be a bit tricky, but first, I guess if you want to try this problem by yourself, you can pause the video right now and just get to code, because I'm going to discuss now how to solve this problem. So before we start, I think it'll be less overwhelming if we just get rid of the edge case. So the edge case would be if the root is null, then simply we just return this empty list. So if the root is equal to none, then we return an empty list. So that's fairly straightforward. And now, as you guys notice, the output is a list of lists. So not only are we adding all the nodes in order, but we also have to distinguish them between levels, meaning that all the nodes or all the values in this sublist correspond to the values of nodes in the same level. So 9 and 20 are in the same level, and 15 and 7 are in the same level because they're in the same sublist. So that's pretty much the main idea. So what do we have to do? So in this case, right, we should be using some sort of data structure that allows us to store data and to use that data store to pop it in the order in which that data was put into the data structure. So instead of last in first out, like a stack, we should use a first in first out data structure. So in this case, it will be a queue. And the idea is also that we can do all these operations in O of one time. So if we add something to the data structure and then we pop something from the data structure, then all of those operations should be done in O of one time. That way it'll be more efficient. And why do we need that? So here's the approach that we will do. We're going to use a deck. That's what's called in Python. It's really a queue. So it's a double-ended queue. That's why it's called a deck. So from collections import deck, that's the data structure that we're going to use. So I'm going to write that down. And now let's explain a little bit of the approach. So the main idea here, right, is that we add the nodes of a level into the deck, right? In the beginning, we're going to begin with a deck having just the root. And then we need something within the deck to tell us, okay, well, this is the last node of a level that you've processed. Because remember, we are adding the nodes from left to right. So whenever we encounter the last node, right, the rightmost node in a level, there should be some sort of flag or way for the program to know, okay, well, this is the last node in that level. So not only are we adding the nodes to the deck as we process them, but we also need to eventually add some sort of like distinguisher between levels. So the main idea here would be to start with a deck with the node 3, right? And then we can use any sort of distinguisher that does not appear in the graph. So in this case, I'm just going to use a null pointer or a null value. So in Python, it's called none. I'm going to use this as a distinguisher. So the main idea here is we're going to keep doing this process until our deck is empty, okay? And while our deck is not empty, what we are going to do is we're going to pop a value that's like in the leftmost side, so the first one that was added to the deck, and that'll be the current element that we're processing. If that element is a node of the tree, right, In the beginning, it would be the node of the tree. Simply what we would do is we would add to the deck all the non-null children that it has. So in the case of 3, we would add the node 9 and the node 20 to the deck. In the case of 9, we would not add any children because it only has null children. And in the case of 20, whenever we process it, then we add the number 15 and the number 7 to the deck. Okay? Now, what happens when the current element that we pop from the deck is not a node? So it's the distinguisher that we were talking about. In our case, it's going to be a null value. When that happens, what we are going to do is first, we need to check whether the deck is empty. Whenever we encounter a non-value and the deck is empty right after we pop that value, that means that we have reached the end of the tree. So there's nothing else to process. So at that point, we simply stop processing, right? But on the other side, what we have to do, and I forgot to explain this when we were processing the nodes. So let me just track back a little bit. Whenever we are processing the nodes, right, we have to keep track of some sort of temporary list that keeps track of the current nodes visited that level, right? So in the beginning, every time we process the nodes of a level, it starts empty. And then whenever we process this 3, then we add the 3 to that temporary list. So while we don't encounter that distinguisher between levels, we just keep appending the values to that sublist. And whenever we encounter the distinguisher, which is the non-pointer, like I said, if the deck is not empty after that, because if the deck is empty, we have to stop processing. But if the deck is not empty, what we have to do now is add the sublist of the values that we've been adding constantly, and then just append it to an overall list, which will contain all the sublist, which is the output that we want to return. Okay, and after that, simply what we have to do is just reset the sublist so that we start with a fresh one. And after that, simply what we do, whenever we encounter the null pointer and the deck is not null, we add again another distinguisher saying, okay, well, we have found another level. So in this case, we simply add a none to the deck. Because whenever we have encountered a none, that means that we have finished the level. So there's another level right after that. So I hope that's clear. I'm going to walk through the implementation again as I type the code. But yes, so let's define the deck first. So we can just say deck is equal to a deck. And it might be a little bit weird, but that's just the way it is pronounced. I know some people might say DQ, but from what I've been reading on the internet, it's actually pronounced deck, like a deck of cards. So we're going to start with a deck like this, right? Like I mentioned before, this is the distinguisher saying anything after this is level 2, or rather the level that goes after this one, okay? And now what we are going to do is we want some sort of list, which is the one that we are going to return, right? And then this would be the current level list. This is the one that I was saying that as we process nodes, we will be appending the values to the current level list. And whenever we encounter that flag, like distinguisher saying, hey, you know, you've reached a different level, meaning that whenever we pop an element from the deck and that element is a none, we are going to append the current level into the toReturn list. And that's going to be the entire process. So while the length of the deck is not equal to 0, or when it's greater than 0, I guess, it's totally fine. Either way works. What we are going to do first is we need to process the current element. So the current element is deck pop left. It doesn't matter if we pop left or pop right, as long as whenever we append in the opposite direction. Right now I'm going to choose to just append, which in Python will be append to the right. And whenever we pop the leftmost element. So for example here, when I call deck.popLeft in the beginning, the element that will be popped will be the root. But if I wanted to pop right, I would have set up my deck this way. And then I would be inserting elements on the left of the deck. And I would have said pop right there instead of pop left, but yes. So current equals to deck.popLeft. That means that we pop an element from the deck and we have to check whether it's null or not. The first case that we're going to handle is simply if it's just a regular node, which I think it's just easier to process. So let's write that one first. So if the current is a node, meaning that it's not a null pointer, then first the first thing that we need to do is just add the value to the current level. Because we're saying, okay, well, we visited this node in this level, so we need to put the value of it. So that's pretty straightforward. So current level dot append current dot val. And after that, like I said before, if it has a left child, then we append the left child to the deck. And the same thing with the right child. It's important that we append the children and not the actual values, because we are going to be checking the children of the children and so on and so on. So the values are not enough to traverse the entire tree. So if current dot left is not equal to none, and I know that this is the same as saying if current dot left, but I just rather write it this way so that the viewers can understand it better. So then we simply append current dot left. And if current dot right is not equal to none, then we append current dot right. So that takes care of the case and when the element that we pop is a node. Now what happens, like I said before, when we encounter the flag element, the one that tells us, okay, you've reached the end of the level. So that would be the other case. So there are two cases for that. We know for a fact that whenever that happens, we have processed some sort of current level list, like we have added some stuff, right? So right when we encounter that, simply what we have to do is to append current level list. So that's the first thing that we do. And after that, we need to distinguish if the deck is now empty, meaning that there's no more elements left. Whenever that happens, we know that we have processed every single node in the tree, because there are no more nodes right after that, which indicates that there's no level after this flag. So if the length of the deck is equal to 0, then simply what we do is we just break the loop. In the other case, what we do is, like I mentioned before, we have to reset the current level because now we're entering another level. So we reset that list so that whenever we add more nodes in the next level, we're not counting the ones from the previous level. We start from scratch. And then after that, what we have to do is simply add another flag to the deck saying, hey, whenever you've processed all these nodes that we've previously processed in here, this is where the level ends, which means that we have to add the pointer, the null indicator to the deck. And that'll be pretty much it. After that, we simply return the list that we want to return, and this approach should work. Okay. There you go. Obviously, runtimes are a little bit inconsistent, but I've tried this problem before, and it beats like a bunch of them eventually, like faster than 97% at some point. But yes, as you can see there, it's good enough. So what is the runtime of this problem? Well, the runtime of this problem is big O of n, where n is the number of elements in the tree. And that is because we visit every element in the tree at least once. So big O of n. And then what is the space-time complexity of this problem? Well, we are storing the value of every single node in the tree and the output. On the other side, we're not using any extra storage that takes a bigger amount of space. I mean, we're using the deck, but the deck at any given level can have at most n over 2 nodes, because in the worst case scenario, right, you have a perfectly balanced tree, which would be, in this case, for example, a tree that has 2 children here besides everything here. So if you have a total of 7 children, I believe the actual equation is something like the ceiling of n over 2, where n is the number of nodes. That's the number of nodes that you can have at the bottom level. So that's the maximum amount of things that we're going to have in the deck. So that's not going to add any extra complexity to the space-time complexity, right? Because it's still an order of big O of n. So the space-time complexity then overall of the solution, it's going to be big O of n. So yes, I hope you enjoyed the video. This one is definitely a tricky problem that I have not encountered, but like I mentioned before, some of my friends have encountered it. So definitely want to keep an eye on. I hope you got this, or at least you understand it now that you watched the video. And yeah, see you in the next video. Thank you so much for watching, and bye-bye.